All right, this is a video lesson for Unit 5, Lesson 4, which is testing a claim about the mean when sigma is unknown. So the big difference between last lesson and this lesson is that sigma is not known. When sigma is known, meaning we know the population standard deviation, we're really able to just use central limit theorem as our test statistic, which is what we did in L3. More realistically, though, we're not going to know sigma in the real world. Normally, what we're going to have is a sample standard deviation, just like we have a sample mean. So L4 is a little bit more realistic than L3 was. The difference between the two is that, and the reason that we always do L3 first, is because L4 is going to use something new. It's not going to use the normal distribution. It's going to use something called the t distribution, which, because of the way we do things on the calculator, you're not even going to notice a difference between the two. So this should be getting really familiar, seeing this, this set of steps. We do this in every hypothesis test. So more hypothesis tests, more of the same in terms of the how-to. So here's our problem. The heights are measured for a simple random sample of supermodels. Crawford, Budchen, Pestova, Christensen, Hume, Moss, Campbell, Schiffer, and Lorenz, of course. That's a very young Lorenz in that picture, so we might need to age him up a little bit. Let's give him some facial hair. Oh yeah, that's starting to look a little bit more familiar. There you go. Let's add a little bit of age to it, a little gray in the beard, a little gray in the hair. All right, there you go. Now you have a much more realistic Lorenz. Nothing else in that picture has to change, of course. So they have a mean height of 70 inches and a sample standard deviation of 1.5 inches. So right here, they're giving us the evidence. Now comes the claim. We have a 0.01 significance level to test the claim that supermodels have a mean height greater than 63.6 inches. We're going to need that information when we get going. Okay, so let's do it. We start with our hypotheses. Okay, our ho and our ha, if you will. Okay, our null hypothesis is going to talk about the mean because we were told that we were testing the claim that the mean height, so it's a mu problem. So mu equals, and we have the number being suggested here is 63.6. The alternative hypothesis is still going to be about mu, and it's going to be the same number, 63.6, but we have to decide what the appropriate inequality symbol would be here. Well, they say greater than 63.6, so it's going to be a greater than symbol. Mu is greater than 63.6. So there's our hypotheses. Now we need our significance level. Well, the problem told us to use a 0.01 significance level. So alpha equals 0.01. And now here's our new test statistic. It looks a lot like central limit theorem, but instead of z, we have t, and instead of sigma, we have s. That's really it. I know I have a fancy little mu here, but don't worry about that. That's just mu. That's just the same mu we've been using. Okay, so there's our new test statistic. So let's start writing that. T equals our x bar. That's going to be our sample mean. So I go up to the sample, which I kind of highlighted in pink here. Okay, and we're looking for the sample mean. The sample mean is going to be 70 inches. Then we need our population mean, which has been suggested to be, by the null hypothesis, 63.6. So minus 63.6 divided by, we need our sample standard deviation here, which the sample told us our standard deviation is 1.5. So that's our sample standard deviation, 1.5, divided by the square root of the size of our sample, which if I come back up here, the size of our sample is, well, they didn't tell us, but I can count because it's 1, 2, 3, 4, 5, 6, 7, 8, 9 supermodels. So 9 is the sample size here. So there we go. We're set up to go figure out our test statistic now. So t equals, I'm going to go to my calculator. I'm going to put parentheses around 70 minus 63.6 divided by the square root of, divided by parentheses 1.5 divided by the square root of 9, close parentheses, and I'm getting an answer, it's a big one, I'm getting an answer of 12.8. Now, t is a little bit different than z, so don't assume that this is going to be a sure thing rejection just because that's a really big t. Okay? Now, we are going to figure out the p-value using the same method that we've used before. Okay? We're going to draw t as if it's z. They're very, very similar distributions. So just draw it as if it was z. We're going to put 12.8 over here. We're going to shade. It was a greater than problem, if I remember correctly, saying supermodels have a bigger height than 63.6. So we're going to shade to the right. Now, instead of saying normal CDF, we're going to say TCDF. And then we're going to follow very similar steps. So TCDF is in the same location as normal CDF, and we're going to calculate this very, very similarly. Our left bound is going to be 12.8. Normally we use 10 to represent infinity. Because I'm not so sure of this t distribution, it's a little different. Let's use an obnoxiously large number to represent infinity, just to be sure. Let's use 9999. Okay? And then for this, it is a little bit different. So instead of writing 0 and 1 next, they're going to ask for degrees of freedom. The degree of freedom rule is that we're going to use n minus 1 for degrees of freedom. So remember n from our sample size? Our n in this problem was 9. Okay, it said it or we counted it off in the problem. So we're going to do 9 minus 1 equals 8 as our degrees of freedom for this problem. So t is a little bit different. It's not going to be always 0 and 1. You're going to have to find what's called degrees of freedom, df, and that's always going to be n minus 1. Okay, so we got TCDF 12.8, 9999, comma 8. So let me go to my distributions. I have to slide down a little bit to find TCDF instead of normal CDF. I put in 12.8. Upper bound, I'm being obnoxious and putting 9999 to represent infinity. And then 8 is my degrees of freedom. And I'm getting a really, really small number back. It's pretty close to 0 plus. But I'm going to put point, then 6 zeros, and then 6, 5. And what this means is when you have a p-value that's this small, okay, this is our p-val. When you get a p-val that's this small, it's going to be really easy to reject because it's obviously going to be less than alpha. So don't be surprised when you get really small p-values. It just means you're going to confidently reject. So here's the problem. We're supposed to, or the conclusion. We're supposed to reject if the p-value is less than or equal to alpha. Well, our p-value was super small. What was it? 6, 5. Super small. Less than, at the beginning of the problem, we set it as 0.01. This is true, so we're going to reject the null, which means we're going to say the alternative is true. When we reject the null, we say the alternative is true. So let's put that in non-technical terms. There is enough evidence to suggest at the 0.01 significance level that, and then alternative hypothesis in words, supermodels have a mean height greater than, if I remember correctly, it was 63.6, but I'll go back and check, and yes, it is 63.6 inches. So when you reject the null, you say the alternative's true. And there we go. So now we got one more problem. It's going to put everything together. It's a little bit longer of a problem because you're going to have to use your calculator. It's not too bad. But the claim here, manufacturer advertises that the average life for light bulbs is 900 hours. So that's the claim. The average life is 900. Okay? And then they want us to test this at the 0.01 significance level. Okay? Well, this time you notice they didn't give us any actual sample statistics. They didn't tell us an X bar or an S or anything. What they did do was they gave us a data set. And what we can do with that data set is we can go find the things we need to do. So what I'm going to do before I get this problem going is I'm going to go to Stat Edit, and I'm going to put those data values into my calculator. So 9995, 590, 510, 539, 739, 917, 571, 555, 916, 728, 664, 693, 708, 887, and 849. So I've put those all into my stat edit. There should be 15 of them. And I'm going to do those stat calc 1var stats that I'm used to doing. And I go and I run the 1var stats on it. And I'm going to leave that up on my calculator for now because I'm going to need it when I get going on this problem. So we're going to go about the whole process here. Null hypothesis. Well, they're talking about that the average means mean. So we're talking about the mean. They're saying the mean equals, always for the null, and the alternative is going to be the mean and some inequality symbol. Well, we're going to go with the mean is 900, according to the claim. And the claim doesn't say greater than or less than, so we always do not equals to when that happens. So the alternative is going to be it doesn't equal 900. Our alpha for this problem is going to be 0.01. Now, the big question, what test statistic do I use? For mean, we learned yesterday to use a Z1, and today we learned to use a T1. And it was all about whether or not we knew sigma. Well, if they don't tell us sigma, we don't know it. So if they give us evidence, like this data table, but they never tell us what the population standard deviation is, we have to use the sample standard deviation. And if we're using the sample standard deviation, that means we need to use T as our test statistic. So we've got T equals X bar minus mu over S divided by root N. So I'm going to have to use the T1 because I don't know sigma. Okay? Now, what is X bar? That's why I ran the 1var stats on my calculator. I looked to my calculator. It says X bar is 724.07. So that's straight from my calculator. That's where I got that info. Okay? I'm actually going to go and move this down here for spacing. And then the mean, let me scoot that around. My mean for this problem, according to the hypotheses, is 900 divided by my S. I'm going to go back to the calculator. Calculator says S is 156.92 divided by the square root of the sample size. Well, the sample size was 15. They told it to us here, and you could also count how many data values are here. So that's over 15. And let's see what we end up getting back for T. We're going to get T equals, and I'm going to put into my calculator, parentheses 724.07 minus 900 divided by parentheses 156.92 divided by square root of 15. And what I should be getting back is negative 4.34. So I've got my hypotheses, I've got my significance level, I've got my test statistic. Now we're going to go get a p-value. So for the p-val, we're going to start off by drawing a picture. Negative 4.34. Now, for a not equals to, just like it was with z, we're going to go to the left if it's negative or the right if it's positive. This is a negative, so we'll go to the left. But for not equals to, we go to the left and we multiply by 2. So, how's that going to look when we do this? It's going to be TCDF left bound, which we could go back to calling it -10, or we can call it -9999, whatever you want to use for infinity with t, okay? I'm going to keep calling it -9999, just because t's can get weird, and I just want to be sure that I'm way to the left. So -9999, -4.34, and then remember degrees of freedom, not 0 and 1 anymore, but degrees of freedom. And the degrees of freedom here are n minus 1, so 15 minus 1, which is 14. And then remember, we have to multiply this by 2 because it's a not equals to problem. That gives us a p-val of, let's go to our calculator, TCDF, lower bound -9999, upper bound -4.34, 14 degrees of freedom, times 2, gives me an answer of 0.000679. So I've got my t, I've got my hypotheses, I got my significance level, I have my p-val. Now it's time to make a conclusion. Just trying to separate everything here, okay? So we're going to ask ourselves here in this non-technical conclusion, we're going to say, or sorry, this technical conclusion, we're going to say, is the p-val less than or equal to alpha? Is 0.000679 less than or equal to 0.01 significance level? And it's yes. So we will reject the null hypothesis again, just like the first problem. We'll reject the null, and our final conclusion will be there is sufficient evidence at the 0.05, or sorry, at 0.01 significance level to show that light bulbs do not have an average life of 900 hours. And the reason we're saying do not is because we're talking about the alternative, and the alternative says not equal to 900. So we're saying it does not have an average life of 900 hours. And that's it. That's everything to know so far about hypothesis tests when we are not knowing sigma. So everything in this lesson was a mean hypothesis test for when we didn't know sigma, and we had to